Hi, welcome to Math 1300, Nunez Community College. Today we'll be doing section 4.2. 4.2 is polynomial functions. Polynomial functions are the functions that we have been studying the last several sections. A polynomial function is a function that is both smooth and continuous. A function that is both smooth and continuous. Since it's continuous, we have arrows on each end. Smooth, meaning that it has waves, but no jagged edges, okay? This would be an example of a polynomial function, smooth and continuous. It's in the form of f of x equals a x to the n plus b x to the n minus 1, meaning if this was 4, this one would be 3, and so on and so on. C x to the n minus 2, dot, 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 all the way down to a letter or a constant where n is to the 0 power. Now, we are going to ultimately graph these polynomial functions. What does a polynomial function not look like? Well, if it has things like, let's say it's coming up here and it does this. This point is called a cusp. It cannot have a cusp. Suppose it's continuing and suppose it stops here and jumps up a bit. This is called a break. It cannot have a break. Again, smooth and continuous, it keeps on. And suppose we continue and then there's just a open dot. This is called a hole. So the things that a polynomial function cannot have is it cannot have any jagged edges called cusps. It cannot have any breaks where it jumps to another level and continues. And it cannot have any open dots where it's a hole and just jumps over. We are going to graph them. We don't really need to know too much about what they're not. We need to worry more about what they are, okay? But in order to graph them, we are going to find something called the zeros of the function. We're going to find the zeros of the function. The zeros of any function means where the function crosses the x-axis. If it's doing this, then every place that it crosses the x-axis are called my zeros. Here, here, and there. In order to find the zeros, we take the function, we factor it, and we solve for the x's. When we solve for the x's, the answers would be our zeros. The answers would be our zeros. So in the first example, they want us to find each zero of the polynomial function. Find each zero of the polynomial function. And they give us, we're going to have functions that we can factor. So we will be able to factor these functions. Matter of fact, a lot of them will be factored for us already. So that's good. But if not, we might have f of x is equal to x to the third plus 4x squared plus minus x minus 4. Minus x minus 4. This function here, if we're trying to find the zeros, we're going to factor that. Now this being a 4-term polynomial, we factor a 4-term polynomial by grouping. So we're going to group the first two together and the last two together, and we're going to factor out what we can factor out. In the first one, we have x to the third and x squared. We can factor out an x squared. And if we do, that's leaving me with x and then plus 4. X plus 4. Factor out an x squared on both terms, I'm left with x plus 4. On the second term, I can factor out a -1. And if I factor out a -1, it changes both signs. So this will be positive x and plus 4. When we factor by grouping and we factor something out, what's left has to look identical. Has to look identical. And if so, then we put the two terms that we factored out together. That's going to be x squared minus 1 times x plus 4. So what we've accomplished so far is we have factored out a binomial from this whole thing, and this is what's left. But this is still x squared. Since it says x squared, this binomial here should be able to be factored again. And it can, because this is known as the difference of two perfect squares, the difference of two squares. So we can factor this down to x plus 1 times x minus 1, and then we still have times x plus 4. These are going to be the zeros of the function. Because again, if we're looking at where it crosses the x-axis, I know that this is equal to 0, the actual f of x. So in order for that to be true, one of these has to be 0. So x plus 1 equals 0, which means x equals negative 1 when I solve. X minus 1 equals 0, so therefore x equals 1 if I solve. And x plus 4 equals 0, so x equals negative 4. These are the zeros of the function. These are the zeros of the function. And if I was graphing this, which is going to be in a couple of steps or a couple of more examples up, we would know at negative 4, it would cross. We would know at negative 1, it would cross. And we would know at 1, it would cross. So we know that if we were graphing this, and this was our function, that would be 3 points that we would put on our graph. That would be 3 points we'd put on our graph. Okay, another example where we're trying to find the zeros may be f of x is equal to x to the 5th minus f of x is equal to x to the 5th minus 9x to the 3rd. Again, with this, we're trying to find the zeros. Find the zeros. By the way, the highest exponent tells us how many possible zeros we could have. On the last example, we had x to the 3rd, and we had 3 zeros. Here we have x to the 5th, so we could possibly have as many as 5 zeros. You don't have to have 5, but we could have 5. So for this one here, I'm going to factor, and I'm going to factor out what? X to the 3rd is the highest x that I can bring out. So I'm going to factor out x to the 3rd, and I'm left with x squared minus 9. X squared minus 9. For this one, I'm trying to factor it into x's to the 1st power. So x to the 3rd would be x times x times x. And then x squared minus 9 is the difference of two squares. That would be x plus 3 and x minus 3. So again, we're trying to multiply together, get it equal to 0 because that's where it crosses the x-axis. These three are the same, so I only have to do one of them. That means x equals 0. That would satisfy this. The other one would be x equals negative 3. That would satisfy this. Or x equals positive 3. In this case, we only had 3 zeros, but we could have had 5 if these three things had all been something different. We could have had 5. Okay, from here, we're going to look at finding the end behavior. Because so far, we know that we can find the zeros. Negative 3, 0, and 3. And we know it could be passing through those circles. But what happens in the end? Well, we have something that's going to help guide us. The end behaviors could be where both ends are facing up, or the end behavior could be where both ends are facing down, or the end behavior can be where the left is facing down, the right is facing up, or even the right is facing up and the left is facing down. We have all those options. So we have something that helps us, that's going to tell us what the end behavior is going to be. The end behavior is going to be from the first term of the function. F of x is equal to ax to the n plus bx to the n minus 1, and so on and so on. That's what we said when we talked about a polynomial function. Well, the end behaviors comes from this. The end behaviors comes from the portion that has the highest exponent. The portion that has the highest exponent. The first thing that we're going to look at is the exponent n. So this is the end behavior. We look at the n. So it's ax to the n. N is either going to be an even number or n is going to be an odd number. N is going to be an even number or an odd number. Even number meaning like x to the second power, x to the sixth power, x to the 10th power. That would be even. Odd would be like x to the third power, x to the first power. That would be odd. If n is even, we could have one of two scenarios. So n is even. If n is even, we then look at the coefficient a. We look at the coefficient a. If a is a positive number, then both arrows face the same way. They both face up. So n is even and a is positive, both ends go up to infinity. If n is even and a is negative, then both ends face down. But if we have an even exponent, both ends face the same way, whether it's facing up, or both ends face the same way, whether it's facing down. The other scenario is if n is an odd number. If n is an odd number. Well, if even means they both face the same way, then odd means they're going to face opposite ways. N is odd. N is odd. In the first case, we're going to have n is odd, but a is positive. So we have a positive a, okay? In that case, it's like a positive slope. So on the left, it faces down, but as we go to the right, it rises. And if a is negative, then it's like a negative slope. The left faces up and the right faces down. So now we can find the zeros where the graph is passing through, and we know what the ends are actually doing. Eventually, we're going to be able to graph this whole thing. So, for the example number 2, they want us to take the function and they want us to find the end behavior. Take the function and find the end behavior. So the function that's in question is going to be f of x is equal to 4x to the third. F of x is equal to 4x to the third minus 2x plus 1. In this case, we're looking for end behavior. The only thing that matters is going to be the 4x to the third. The rest of it is just tag along, if you will. So, in this one here, our n is 3, so our n is odd. And our a is 4, so our a is positive. So therefore, what do we have? The end behavior is going to be rise from left to right. Because odd is different and positive is a positive slope. Okay, suppose we have an example where we have f of x is equal to negative 2x to the fifth plus 4x to the third minus 1. Again, all the stuff on the right does not matter. It's only the first coefficient. So we got what? N is odd and A is negative. So therefore, from left to right, it falls. So on the left, it faces up. On the right, it faces down. Okay, suppose we have that f of x is equal to 5x to the fourth minus 2x to the third plus 3x squared plus 4x minus 10. Again, it's a big polynomial function, but we're looking for the end behavior. All we're looking for is the first term. So we got what? N is even, which means they're both facing the same way. And A is positive, which means they're both facing up. So again, the end behavior is going to be like this. And then on the last one, suppose I have f of x is equal to negative 7x to the sixth. And that's all that we have. In this case, we have what? N is even, which means they both face the same way. And A is negative, which means what? They both face down. They both face down. So again, we have the zeros and we have which way that the function is ending. Which way that the function is ending. The next thing that we have is something called multiplicity. 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 Multiplicity is meaning or means how many times each zero occurs. How many times each zero occurs. How often the zeros occur. How often the zeros occur. It's going to be a number, but that number is going to tell us something. So it says, find the zeros of the function and determine its multiplicity. Most of the functions will be factored for us already, which is good. And we're going to look at it. Suppose I have f of x is equal to x minus 3 times x minus 1 squared times x plus 2. We want to find the zeros, which we can do from here because it's already factored for us. And then they want us to find its multiplicities. What we usually do for this is we make ourselves a sign chart. So I have the zeros, and I'm going to have the multiplicities. The first zero we have is this one, and this would be 3, because 3 minus 3 gives me 0. The multiplicity means how many times do we have it. This x minus 3 is to the first power, so its multiplicity would be 1. The next one that we have is going to be 1. 1 minus 1 is 0. The multiplicity, though, is going to be 2 because it occurs twice. It says squared. And then the last thing we have is going to be negative 2. Negative 2 plus 2 is 0, and its multiplicity is also 1. So that would be filling out a sign chart on the zeros and its multiplicities. Now, the reason that we're doing a chart is because the multiplicity tells us something. 0 is a 3. 0 is a 1. But the multiplicity differences means something different happens. If the multiplicity is odd, in this case, these two are odd, so the 3 and the negative 2 would be odd. If the multiplicity is odd, then the graph crosses the x-axis. It crosses the x-axis. And I'll show you that in just a second. If the multiplicity is even, for instance, the 1, that 1 happens twice, so that's an even multiplicity, then the graph, they call it touches or bounces. Touches or bounces. So it would touch the 0 and then go back the other way, or bounce back the other way. So they want us to take the 1 that's right here, and they want us to graph it by using all of the things that we've learned. And I'm going to show you the multiplicity in just a second. They want us to graph it. So since we already have this as our function, we know our zeros, I know my multiplicities, I need to find the end behavior. But before I do, I'm going to put the zeros down. I have at negative 2, I have a 0. I have at 1, a 0. And I have at 3, a 0. We know that. I want to find my end behavior. But in order to find my end behavior, I need f of x equals ax to the n. This is already factored for us. This means when we put it all back together. I know one thing. If I multiply this times this, I'm going to get a larger polynomial. And then if I multiply that by this, I'll get an even larger polynomial, right? But the thing is that the x is all positive numbers. So therefore my a is going to be positive. There are no negatives to multiply or n. So I know that my a is going to be positive. So I know that whatever happens with the n is going to tell me whether I'm facing both the same way up or if I'm rising from left to right. Now the n means how many do we have here counting multiplicities. This is a 1, this is a 2, and this is a 1. So that's 1 plus 2 is 3, 3 plus 1 is 4. Or I can look in here and add it. 2 plus 2 is 4. So that means the n is equal to 4. If I multiply all these together, I would have x to the 4th power. So it's telling me my multiplicity is, it's telling me that my n is even. So therefore, we have a positive, we have even, so I know that both ends are facing up. I know that both ends are facing up. Now I know we're going to pass through this, and this, and this. However, the negative 2, which is the first one we see, has a multiplicity of 1. We said when it's a multiplicity of 1, I'll put C and T for crosses and touches. It crosses, and it touches. Because we said odd multiplicities cross, even multiplicities touch. Which means if it crosses, that means it actually touches and goes through to the bottom. And then we know that it does something and comes back around. And here at the 1, it touches. So here we'll go up, touch it, and bounce back down. Now I'm leaving a little gap because I don't know how far to go, but we're going to learn that in just a second. And then we have the 3. The 3 has a multiplicity of 1, so therefore it crosses again. So it does something, and then when it comes back up, it crosses and goes through. So we take our zeros. We know whether it's crossing or touching. I know my ends, both facing up. But now how far down does it go? Well, for this one, I might try to test 0. I'm going to test the number in between the zeros. So if I test this, this is what? The y-axis, so I know x equals 0. So in order to do that, I'm going to find f of 0, which means where at does this thing go when x is equal to 0? That's going to be 0 minus 3, 0 minus 1 squared, and 0 plus 2. That's going to be what? Negative 3. Negative 1 squared is 1, and plus, so multiply by 2. So that's going to be negative 6. F of 0 equals negative 6. So at negative 1, 2, 3, 4, 5, 6, we know that it's crossing the x-axis. So we can connect up this dot and connect that up to show how low it goes. And how low does it go here? Well, I got a number in between these two zeros. This number is 2. So I'm going to find f of 2 to see exactly how far down it goes. So I'm going to plug 2's in for the x's. So I have 2 minus 3 times 2 minus 1 squared times 2 plus 2. So 2 minus 3 is negative 1. 2 squared, 1 squared, that's going to be 1 times 4. That's going to give me negative 4. So f of 2 is equal to negative 4. So negative 1, 2, 3, 4. That'll be my point there. And this, after we connect it up, is about what that graph would look like. You're going to have to, in Cengage, be able to determine which graph it is, and you're going to have to look at it and be able to determine. But when you are looking at how low down it goes, think about what's going on. All we're doing is plugging in the x at that number, and it's telling us exactly where the y is. Plugging in the x at that number, as in plugging in that number for x's, and it tells us where the y is. But that would be graphing the polynomial function. That would be graphing the polynomial function. The next example, we have one more. This time, we're graphing a function that's not factored for us. We have to factor it ourselves. So we're going to have f of x is equal to x to the third minus 4x. X to the third minus 4x. Since it says x to the third, we know some things. For one, it's got an odd exponent. I know my a is going to be positive. I know we can only have 3 zeros or less. So we're going to have some organization with this. So the first thing we're going to do is step 1, find the zeros. Find the zeros. So if I factor this, this is going to come up to be f of x is equal to x times x squared minus 4. Factor an x out of both of them. And then this factors down to x times x plus 2 times x minus 2, because this is the difference of 2 squares. And then we know what? That x equals 0, x equals negative 2, and x equals positive 2. So that would be our zeros. 0, negative 2, and positive 2. And we can go ahead and put that on a graph as we find out what numbers we have. Negative 2, 0, and positive 2. Okay, now we're at step 2. Step 2 is going to be the end behavior. The end behavior. the end behavior. And the end behavior in this case, we're going to look at this, which is what? X to the third. And x to the third is going to be what? A is positive and n is odd. So if it's positive and it's odd, then we are going to what? We're going to have opposite ends, and both of them are going to be positive slope. So it's going to be coming from the left and going off to the right. Then we're going to look at step 3, which is the sign chart. So in the sign chart, we got our zeros. One of these days I gotta get new markers. We have our multiplicities. And we're gonna have our crosses or touches. For our zeros, we have 0. That multiplicity is 1. If it's 1, it crosses. The second one we have is -2. Multiplicity of 1, because we only have one of them, therefore it crosses. And then we have a 0 of 2, multiplicity of 1, and it crosses. So each one of those cross. So it crosses, and it crosses. But what we want to know is how far down or how far up. So now we're going to look at plugging in some numbers. This is -1, so I'm going to find f of -1. That's going to tell me how high up it goes. This is 1, so I'm going to find f of 1. That's going to tell me how low it goes. All I'm doing is plugging these numbers into the x's to see how high and how low it goes. So if I have -1, that's -1 to the third, which is going to be -1. -1 to the third minus 4 times -1. So it's -1 to the third is -1 plus 4, which gives you +3. So at -1, it goes all the way up to +3. So that's where it's making its turn, coming back down. And then at +1, I have what? 1 to the third minus 4 times 1. So that gives me -3. So it goes down to -3. That would be where it's making a turn. And again, this is what we're trying to do. We're taking the polynomial functions, again, which is smooth and continuous. We're finding its zeros. We're taking the zeros and we're doing the end behavior, finding the multiplicities, and we're crossing, touching, and actually connecting them up and graphing the polynomial function. This has been section 2.4, polynomial functions, and I'll catch you at the next one.